Hi, and welcome back. My name is Andrea Alberti, and together we will understand the basics of Earth observation, what it is about, what enables it, and its potential. This module will be followed and strongly complemented by a series of lectures from specialists that will demonstrate the full potential of Earth observation as a powerful toolkit to analyze the Earth's surface. What is Earth observation? Intuitively, we are into a space economy course, and we might conclude it is about images from satellites, or about a collection of information about the Earth. We have all seen pictures from satellites in our lives. Whether we are looking at the news, and sometimes the most dramatic scenes are represented. Whether we are using Google Maps, for example, to check out our next holiday destination, or we are picking a restaurant. The representation of the message we are fed with is supported very often by visual information from satellites. Satellite imagery. So, is this all about Earth observation? Most formally, Earth observation is defined as follows. Let's read together. Earth observation is the gathering of information about planet Earth physical, chemical, and biological systems. It involves monitoring and assessing the status of, and changes in, the natural and man-made environment. And why Earth observation is important? Human civilization is having an increasingly powerful influence on the Earth system. Earth observations are invaluable for assessing and mitigating the negative impacts. More concisely, Earth observation delivers information to enable fact-based decisions. And please note, I indicated information. We all should be aware that data is not information and information is not knowledge. So, Earth observation is indeed about satellite imagery and satellite data. But it is not only about that. Let's step back to the examples we saw before. Most of what represented here is way beyond a simple picture. A mine waste map, volcano eruption, trenches digged across an airstrip, human activities at an airport, and much more. These are all visualization of processed data, combined with other data and information, so to generate a representation that provides us concise information to our eyes. Processing takes place to combine data from different sources and deliver us interpreted, organized information about the event we are interested to look at. Google Maps does not only provide satellite images, but merges data of different sources, traffic data, elevation models, feed from the people to provide us an integrated platform that delivers us multiple information about the location we are observing. We are starting to understand that Earth observation is more than just pictures. It is an ecosystem of products and services that leverages on Earth observation satellites, but not only. Earth observation satellites are the necessary space infrastructure at the core of this ecosystem. But satellites alone deliver data. The Earth observation ecosystem requires access to the data, analytical models and data-driven methods to crunch the data. One may need complementary information to compile the products and services that we want to deliver. And we need ground truth observation to validate our products and services. And finally, we need stakeholders that allow this ecosystem to be active and prosperous. So, let's start to concentrate on space infrastructure and on the access to data. Earth observation space infrastructure can be widely different. We span from CubeSats constellations as the Planet S Flock, the Spire Lemur, or ICEYE, to constellations of medium-sized satellites as the Satellogic NuSats or the Planet S Rapid Eye, to the large and complex satellite systems as the Worldview, the METOP, or the Sentinels. There are about 30 commercial Earth observation constellations that are operational nowadays, and more than 100 that are planned or in preparation, not accounting for institutional satellites. There are many subsystems that compose a satellite, but at the core of an Earth observation satellite, we find the payloads, also called instruments or sensors. We can classify Earth observation payloads in different manners. Here we classify them as active or passive payloads. Let's start to look at passive payloads first. Here, the sensors rely on capturing the radiation that leaves a target, either because of the sun radiation that is being reflected by the target, or because of the thermal radiation that is being emitted by the target itself. These payloads are working much like a traditional photographic camera, without the need for an active man-made stimuli. Let's start to look at some typical passive payloads. And to do this, we use a famous case that happened in March 2021, when the Ever Given container transport ship got stuck into the Suez Canal. We have optical passive payloads that deliver panchromatic, that is, black and white data, mostly in the form of pictures and in some cases of videos. These payloads are generally delivering fast-rate data and with higher ground resolution. That means smaller pixels on ground. Passive optical payloads can also deliver data with spectral content. These payloads are generally called multispectral sensors. A normal color image delivers us with 3 spectral bands, the red, the green, and the blue. In addition, many payloads offer additional spectral bands, let's say additional colors, in the visible and in the infrared range. The payloads that generate multispectral content are substantially highly sophisticated cameras equipped with special imagers, depending on the technology and on the design solution adopted. For example, here, a series of filters are placed right in front of the imager. Or here, a series of independent imagers are equipped each with a dedicated filter. Multispectral payloads typically operate in the visible and in the infrared region, and are present, together with panchromatic payloads, on many institutional and commercial Earth observation satellites. Hyperspectral sensors are instead highly sophisticated payloads that are able to distinguish a much more detailed spectral content of the scene under observation. Multispectral sensors provide a limited amount of bands, or colors, to the users. Hyperspectral sensors, instead, provide a highly resolved spectral content, very often in a continuous fashion over a portion of the electromagnetic spectrum. The design and development of a hyperspectral sensor is generally very complex, and they are mostly built through institutional funding. Hyperspectral imagers, together with multispectral imagers, support the generation of so-called data products that offer the ability to understand our environment well beyond what meets the eye. These payloads actively contribute to monitoring atmosphere, water, vegetation, forestry, land use, mineralogy, and much more. In this example on the left, it is visualized the measured increase in sulfur dioxide gas emission as the Suez Canal was blocked by the Ever Given. Commercial ships were being hoteling at the entrance of the channel in the Mediterranean Sea. While here, on the right, we see the evolution of total suspended matter in the water of the channel during the Ever Given blockade. Total suspended matter directly relates to the water habitat quality. Active payloads rely instead on the ability to capture the radiation that has been first generated by a man-made active piece of equipment. This radiation is directed to a target and is then reflected back to a sensor. There are active payloads that operate in the optical domain as LiDARs, and there are active payloads that operate in the radio domain as radars, synthetic aperture radars, and radio occultation payloads. In general, active payloads that operate in the radio domain look very different from a camera or a telescope, but still, they embed technologies that allow us to monitor and observe the Earth's surface. Let's look at some of the products of synthetic aperture radars. Because of the different nature of the payload, and because of the different wavelength at which they operate, synthetic aperture radar can observe the Earth's surface at night or irrespectively of cloud coverage. This offering is a strong complement to the capabilities of optical passive Earth observation methods. Synthetic aperture radars do not only have the ability to see through clouds and at night, but can also measure elevation changes. This is functional to detect and to monitor water floods, as in this example from the startup ISI, land subsidence, and human and industrial activities. And here, another example of the ability of synthetic aperture radars to monitor the ship traffic accumulating at the south entrance of the Suez Canal. A last example of active payloads, maybe spurious, as it is a crossover between different domains, are the automatic identification systems. Instead of monitoring the active signal generated by another satellite, automatic identification systems detect the active signal of aircrafts or ship transponders and locate them on the Earth's surface. This technique contributes to monitoring and assessing man-made activities. For both passive and active payloads, there are characteristics that define their complexity and cost, and help us to better understand their technical offerings and to decide which type of data are more helpful for our purposes. These characteristics will be discussed in depth in other modules. Let's focus instead on size, weight, and power. If we want to build and deliver a payload, or if we want to host a payload on our satellite, the allocation of size, weight, and power is crucial to define the cost of the equipment and its performance. Miniaturization of technologies plays an important role. But for Earth observation payloads, laws of physics rule the dimensioning of the equipment. As a rule of the thumb, the larger the payload, the higher the cost of the payload, the better the performances we can expect. Nevertheless, we should ask ourselves what the targeted end user really seeks in terms of data quality. Over time, the performance of Earth observation payloads has been improving dramatically. Payloads have been able to acquire better resolved, more detailed scenes. At the same time, the ability to download data from satellites and consequently the data rates has been highly increased to cope with the increased resolutions. As we start to talk about data, let's look at how to access them. Access to data is a key enabler of the overall Earth observation ecosystem. We can distinguish two main approaches: the open data policies and the commercial policies. Up to year 2000, access to satellite data was limited and costly. But since year 2007, a wave of policy changes has been adopted by the main institutional providers of satellite data that initiated free distribution for the majority of users and scopes. Let's take the case of the data managed by the USGS. Up to year 2007, the cumulated amount of scenes distributed for the Landsat satellites against a fee was less than 1 million overall. But in year 2020, more than 100 million scenes cumulated were distributed, serving users from more than 186 countries. Users also started to change the behavior from a single scene to multiple scene coverage at multiple times for the same location. But the open data policies are not the only way to access satellite data. Multiple commercial operators distribute satellite scenes, and we can identify three major drivers for the costing. The smaller the pixel size, that is, the better the resolution, the higher the cost. At the same time, a coarse correlation is existing between frequent satellite or constellation revisit time, ground resolution, and price per scene. And finally, each commercial entity has a corporate-specific policy that may ease or make more complicated the access to a specific dataset of interest. Having to deal with different data providers can reveal cumbersome, and the role of satellite data brokers is arising as a middleman between the commercial entities and the users. Earth observation data are growing at an incredible pace. An institutional constellation as the Sentinels is downloading more than 20 terabytes of data every day. Commercial Earth observation satellites are estimated to download more than 100 terabytes of data each day. This translates into petabytes of raw data stored each year on public and private servers, data that needs to be backed up, calibrated, processed, scrutinized, analyzed. And here lies the relevance of the Earth observation ecosystems, complemented by analytical models, data-driven models, and data fusion approaches in order to deliver the stakeholders sensible, concise, and understandable information. We conclude on the financial volume generated by the Earth observation enterprises. And we only focus on those companies whose products and services are based on Earth observation data. This was totaling in 2019 to about $2.3 billion US. And this is indeed a small market share, considering the overall investment performed to establish the satellite constellations and to manage them and to manage the data. But we shall have a look at the rate of growth. In this representation, we can see how between 2014 and 2018, the Earth observation share has been one of the most growing segments of the overall space economy. So, let's recap together. Earth observation delivers information to enable fact-based decisions. Earth observation is an ecosystem based on space infrastructure and is complemented by additional expertise and competencies. The added value of Earth observation is to reveal more than what meets the eye. And the final thought. Whereas Earth observation has been used widely by institutions and governments to set and monitor policies, an increasing amount of businesses are using Earth observation products and services for their commercial and financial use. Thank you very much for your attention. Goodbye.